In this video, we're going to derive design equations for the L-match networks from the series to parallel transform equations. We're motivated to use a parallel to series transformation in this network because it isn't easy to analyze in the same way that a parallel RLC or a series RLC network is. However, it's easy to convert CP and RP, which is our load in this example, into their series equivalents RS and CS. And then we have a nice series RLC network that we know how to analyze. We'll go through the design process, which just leans on the parallel to series transform equations from top to bottom. Starting at the first bullet on the page, the parallel to series equation specifies the series resistance as a function of the parallel resistance in Q. That means we'll be matched for some specific value of Q. We know that we want our series resistance to be Z0 in order to match our driving line. So I make that substitution and do a little rearrangement of the parallel to series equation to find that the Q we want as a function of our impedance transformation ratio. Moving to the second bullet, once we know Q, we can use Q of the RLC network and omega naught of the RLC network to find values for our L and CS. We do this just by separating the two equations into unknowns. Finally, on the third bullet, we transform CS, which is a mathematical construct, back to the actual CP that we'll use in our circuit. These design equations aren't too bad, which is nice. However, this derivation is specific to the L match we used. So these design equations won't work for every L match. You can see that because things would start going wrong as early as the first line if we had to do a series to parallel conversion instead of a parallel to series conversion. So you'll need to redo this process for different networks. But the 3 bullets on this slide spell out the steps you'd use for any network. Find your desired Q from the resistor transformation, then find L and C from Q and omega naught, and then finally untransform the reactive component. And I encourage you to try one of the other L-match networks and derive your own set of design equations for it. That would be very good practice. Before we wrap up this video, it's worth noting that these equations get easier if Q is high. We can approximate high Q values as the square root of the transformation ratio, and our capacitor doesn't get transformed significantly when Q is high, which means that we can talk about C instead of CS or CP. Rearranging the design equations from the previous page, we find that the characteristic impedance of the RLC network is equal to the geometric mean of the load and the impedance that you're matching to, which is nice. So in summary, I've provided equations for an example parallel to series L match. And you can see those equations in the middle of this page. It's worth practicing with those equations, but also understanding how to derive them for different L networks. Because we need to mix and match these equations slightly for different topologies. Remember, the trick is always start with Q desired, and then move on to calculating L and C, and finally transforming out of the series or parallel transform back to reality.